morning, everyone. Welcome to another edition of the Finite Element seminar at Lawrence Livermore National Lab. This morning, my pleasure to introduce Nat Trask from the University of Pennsylvania. He was at Sandia previously. He's part of various mimics centers. And he's going to tell us about data-driven exterior calculus. And I guess this is an addition to the title for probabilistic digital twins. Nat, the floor is yours.
Great. Thanks, Sanyo. And it's great to be here. And I'm excited to talk to finite element enthusiasts. I'm at UPenn. I just started here last fall. I still have a joint appointment at Sandia. I'm still involved in the DOE sphere. So a lot of the work that I'm going to present today comes from our Mimic Center. It's called CCROGS, and one of the things that we're interested in doing is building digital twins for systems of systems, which is kind of a catch-all for the kind of things that pop up all over the place across DOE, where you have multiple subsystems that are coupled together. In particular, we think about E3SM a lot as a climate model, but so typically these kind of systems of systems, you're thinking about each submodel coming from a huge legacy code. You want couplers that are non-invasive and so on. So if we're going to build a digital twin of a system of systems, right? We want, you talk to different people, you get a different definition of a digital twin. Specifically, we're thinking about something that a digital model that can make a prediction of a physical system, right? So in some ways, that's just classical finite elements. But we want this closed loop picture where you can make predictions close enough to real time that you can also do real time data assimilation on a certain time scale. So you have self-correcting models. So in order to do that, everyone's excited about machine learning because it does stuff fast. But to do this specific class of models fast, you need the kind of guarantees that we take for granted in finite elements, right? So you need to prove that you get numerical stability, that you get physical realizability, that you'll be able to extrapolate or at least know when a model's wrong, like know what the model doesn't know. And in particular, you need to be able to handle multi-scale data. You need models that are probabilistic plumbing to do UQ and so on, right? So makes sense that everyone's excited about machine learning, but there's a gap that needs to be filled in order to, in high consequence kind of engineering settings, to do it robustly. So if we're going to do that, we need guarantees, like the guarantees that I mentioned. And so it may be that deriving a physics-based model, that's intractable. It could either be that the governing equations are just way too expensive to solve, right? Like climate physics, turbulence modeling, all of those, like the governing equations, but to actually resolve all of the relevant length scales is prohibitively expensive. Or it may be that you're looking at a system where the physics are unknown. So for a lot of material science problems, we look at shock, hydrodynamics, combustion, batteries, semiconductors, and so on, right? So this kind of archetypical problem shows up all over the place. Our objective is to build in some exploitable structure so we can prove something. So I talked about climate. There's some other problems that we look at that have the same sort of system of systems flavor to it. You can look at mechanical assemblies, right? Like a car or vehicle. You have fasteners, bolts, things like that. For microelectronics co-design, when you look at very small scale circuits, you get two-way coupling, parasitic currents, thermal effects, and so on once you're squashing a circuit down onto a very small footprint so that you can't neglect the coupling across, between different transistors and so on. And also I'm involved in a SIDAC center applying these kind of ideas to fusion power, right? In that case, you have a whole hierarchy of different models spanning different levels of fidelity, different length scales, and so on, right? So all of these, right, you need just to motivate that there's a reason why we need a rigorous way to incorporate machine learning if we're going to couple all of these physics together. So the primary tool that we're going to use, we work with graphs. Graph neural networks are very popular right now, but graphs have the same kind of topological structure that a finite element mesh has, and so that lets us play kind of finite element style games. And specifically, the tool that we're looking toward is Dirichlet and Neumann map. So if you can learn a Dirichlet and Neumann map, you can imagine, so the cartoon I have in the top left here, right? You have a bunch of subsystems. You're going to punch out the weakest link, right? The most expensive bottleneck in the system that you're trying to model. And if you can figure out the mapping between the state and the fluxes at the interface between this model and other models, then you can couple things together. This is kind of classical and domain decomposition and hybridizable methods and mortar methods and so on. So the idea is that we're going, I'll get into how exactly we do this, but this is kind of the blueprint that on a graph, we're going to hang a model on top of it. And you can think about nodes of a graph as representing control volumes and edges of the graph as representing fluxes in between control volumes. So this is like dual to maybe a finite volume picture. And we're going to enforce conservation structure, right? We don't want to use machine learning to relearn conservation laws. We know conservation laws hold. The empiricism really lives in the definition of fluxes. And so what we do is we're going to represent fluxes in terms of a black box nonlinear flux, that we don't make any assumptions about the form of that, right? So we're going to use non-parametric models in order to identify a nonlinear flux, but we stabilize it using a gradient flux, right? So think about this a little bit like, by analogy to artificial diffusion and the kind of tricks that we use all the time in finite elements to stabilize methods, right? So we're going to do the same thing now, and that's going to let us prove things, even though we don't know what the actual governing equations are, beyond that they're in conservation form. And this is going to come in two flavors. So if somebody gives you a graph, you can think about circuit models, right? There's a natural graph underneath the circuit. It's the network of the circuit itself. And there's a whole class of models that you can hang. You can hang a model on top of that user-provided network, right? So obviously electrical circuits. We did a lot of work in this front for like radiation-hardened circuits and things like that. But there's also non-electrical circuits and so-called circuit analogy models. So stuff like hydraulic networks, spring dashpot systems for mechanical systems, and so on. Right, but there's a challenge that most data that you're going to come across, most scientific data, there may not actually be a natural graph, right? You may just get a velocity field, right? So somebody gives you PIV or DIC or something, right? They'll give you a displacement field or a velocity field associated with a given problem. And so it's not clear what we mean by a graph. So I'll get into the math and exactly how we do this, but I want to just give this picture up front to make it concrete what the end result is going to be. So we use Whitney forms, which is a classical tool for mixed finite elements, and we use them to define control volumes. But the control volumes, typically you would do that by reference to an underlying mesh. Instead, we're going to take the kind of logistic classification networks that people use in machine learning all the time, like to say, this part of space is dogs and this part of space is cats. We're going to repurpose that to partition space up into a set of control volumes. In this picture on the right, you can see the dashed lines are streamlines for flow past the cylinder. In the background, you can see this sort of 3x3 set of control volumes. And as we train the model, we're simultaneously solving for the partition of space and a set of unknown integral balance equations for what the fluxes are on those control volumes, such that the sum of the fluxes is equal to zero. Right? So we're simultaneously learning the geometry and the physics without knowing what the governing equations are. We just tell it the mass is conserved. In this case, that's something you need to know for potential flow. Right? And it's identifying in a totally unsupervised way that, like, yes, the relevant control volume is this cylinder in the center, and then it's working out balance laws so that the learned model, which is the solid lines, agree with the dashed lines with the data. There's a lot of people who've contributed to this. Xiaozhe Hu, in particular, worked out the original data-driven exterior calculus on graphs with me. It was kind of like our COVID project a couple of years ago. I probably won't talk about the metroplectic bracket discovery, but I'll just say that the kind of geometric, you can use this to learn geometric dynamics. So generalizations of Hamiltonian dynamics and Lagrangian dynamics and so on, including dissipative generalizations. The piece that I'll get to at the end is the stuff we've been working on most in the last year or so, which is, once you have one of these models, how do you plumb it with a model for uncertainty, and it kind of come up with probabilistic extensions. So there's a ton of really talented people who have contributed to this. So first, I'm going to talk about this data-driven exterior calculus. This is kind of like the theoretical building blocks. And what you can think about it is it's div, grad, and curl that you know and love from vector calc, but defined on a graph. But all of your intuition, like undergraduate vector calculus, goes through. They're kind of graph analogs to all these things. So this is a heavy slide. I'm optimistic that since this is a finite element crowd, that y'all can actually get something out of this. So these are the ingredients for compatible finite element discretization. You start with a set of cliques. So a k-clique is an ordered collection of nodes. A zero-clique would be a node. A one-clique would be a directed edge. A two-clique would be a loop or a triangle. And a co-boundary operator, which is these D operators, is a map from a k-clique to a k plus one clique. And a co-boundary operator is just a fancy name for a div, grad, curl. And one example would be the zeroth order graph co-boundary operator, which I've written out here. Right? It's defined abstractly like this, but if you actually evaluate this for a given k, you'll get the graph gradient operator, right? So this is something that lives on edges. It's the oriented difference of the nodes that are on the boundary of that edge. You have the graph curl operator, that's this D1 operator, where you're summing up the little pieces of circulation along the edges of a loop. And so what you have, so for those graph calculus operators, those graph div, grad, curl, they satisfy what we know from vector calculus, that the divergence of the curl is equal to zero, the curl of the gradient is equal to zero, and so on. And so what we're going to see is there's a lot of theory that follows just from that simple relationship. So people call that an exact sequence, right? That the composition of two co-boundary operators is equal to zero. So once you have co-boundary operators, what you would do in the graph calculus is you have what's called a co-differential. That would just be the adjoint of those matrices, right? So the adjoint of a graph gradient, you just take that matrix, you take the transpose of it, that would give you a graph divergence in the same way that we're used to from finite elements, that the div is the adjoint of the gradient. But now this is just at a finite dimensional level, right? We're just working with matrices. So the idea with the data-driven graph exterior calculus is we're going to machine learn an inner product, right? So if you parameterize a set of positive definite matrices, you can define an operator which isn't just adjoint in the little L2 norm, right? Which is what you would do in the usual graph calculus setting. Now we're going to define an operator which is adjoint with respect to these data-driven positive definite matrices. And now you'll set up a set of machine learnable div, grad, and curl, which inherit this exact sequence property. So typically, if you were to look at like a staggered finite volume scheme, these would be what people call the Hodge star operator. This would be like the ratio of a primal base area to a dual mesh length, right? It says something about the relative measure of the mesh entities on the primal and the dual grid. What we're going to do here is we just treat these as abstract numbers that we're just going to treat them as parameters that you're going to train with gradient descent. But we enforce that they're positive, right? The only requirement for the theory to go through is going to be that these parametrized matrices are positive, definite. And this is the kind of thing, if you're familiar with like virtual finite element method and other methods like that, people play these sorts of games sometimes. I wouldn't say this is like particularly mainstream, but the idea is that we just view these metrics as something to be determined, right? It's just a parameter on our model. So there's a lot of theory. I'll blow through this, but I'm just going to rattle off and go, up here in the top right, here's the paper. If you're a theorem proof kind of person, you can check there for the details. I'm just going to rattle off that what you get from this framework is what you would get in like a introductory graduate mathematical finite element course, right? So you get the ingredients of like a Lax-Milgram theory. So you can, on this graph, you can define what's called a combinatorial Hodge-Laplacian. We're probably all familiar with the lowest order case where k is equal to 0. This would be like a weighted graph Laplacian where it's weighted by the entries of this metric A. You get higher order versions of this, similar to like a vector Laplacian is like a curl plus a div grad, right? That would be the k equals 1 case and so on. It goes upward. So with these building blocks, right, you start by showing what I claimed, that the derivative of a derivative is equal to 0, right? Curl of the gradient is div of curl is equal to 0. That these adjoint operators inherit the same property. Once you have these derivatives and their adjoints and they have an exact sequence property, you get a Hodge decomposition. So you can decompose an arbitrary vector field into like the gradient of a scalar potential plus the curl of a vector potential plus a harmonic form. You get a Poincare inequality. And then once you have all of those things, you get the usual thing that you would get in a Hodge-Laplacian. You can say that you would get in a Lax-Milgram theory. You get that a Hodge-Laplacian is positive semi-definite. It's invertible. It's unique. As long as you work perpendicular to the null space of the operator. So it's probably a lot, but so if you're not theoretically minded, the punchline is we have machine learnable second order elliptic operators defined on a graph, and we can prove the usual stuff that we can with the finite element method. Okay, so once we have that, we can consider this broad class of models. Right, so you start with a conservation law, and in the k equals 0 case, this basically says like the divergence of the fluxes is equal to the sources. But then you have higher order ones. These would look like gauge conditions when you pick a gauge and you're doing electromagnetism. But if you're not familiar with that, just think of divergence of fluxes is equal to sources and sinks. Then we have this generalized flux equation, and in the HDiff case, this is some of the fluxes is equal to the sources. If you're working on an H curl problem, this would be like conservation of circulations and so on, right? That's what you would get for magnetic field, for electromagnetism, or for vorticity if you're working with fluids. So what we're going to do is we're going to decompose that into a gradient flux plus a black box nonlinearity. And then what you can show, and I'm skipping a lot of steps here, but what you end up with is you get a nice invertible bilinear form. This basically comes from if you take this term here and you substitute it into here, you can identify that this whole piece gives you a Hodge-Laplacian, right? So that Hodge-Laplacian gives you an invertible bilinear form that you can prove a lot about, right? And that has all of these metric terms, all these Hodge star looking things buried inside of it. And then you have a nonlinear perturbation, right? So if you can prove that a model of this form is well posed, so it has a unique solution, then it means that it's fair game to use equality constraint optimization, right? You need to know that there's at least one solution in the set of candidate models, right? And then you can come at this with the usual kind of PDE constraint optimization approach, like you solve a forward problem for the current guess of the model, you solve an adjoint problem for Lagrange multipliers, then you update the model, right? But in order, so there's two important things. One, first you've got to show that a solution exists, but then if it does exist, that means that this conservation structure holds no matter how poorly you're actually fitting the data, right? So that means if you only have like one data sample, or you only take one step of gradient descent, right? Your accuracy may be very bad, but the stability and the structure preservation of the model is guaranteed. So the important thing is that because you can show that this, that elliptic bilinear form A has a Poincare inequality. And if you make some mild assumptions on the nonlinearity, basically just that it slip shits, as long as the Poincare constant is large enough relative to the Lipschitz constant, then you can prove this. Right, so there's a rabbit hole I could get into about how you can guarantee this property during training, and whether this property will hold. Right, as you get to extremely nonlinear systems, it's less likely to hold for trying to fit a model to moderately nonlinear problems. You don't need to do anything at all, right? The data just kind of keeps it in a regime where this is satisfied. But basically what it comes down to is for your neural network, you just want to choose nice Lipschitz activation functions, and then you can enforce this. Okay, so that's, this is older work. That was about 2 years ago. To actually do it justice, I would talk about that for a whole hour. But to me, the exciting thing is what we're doing. How do you actually learn a graph from data, right? That just tells you if somebody gives you a graph, how do you hang the model on top of it? Okay, so in order to do this, we're going to use Whitney forms. And what I'm going to do first is briefly review how Whitney forms are typically constructed. So in general, you would start with a simplicial complex, so like a Tet mesh, and you would start with barycentric coordinates, right? So just think about like P1 finite elements that have this property that the shape functions reproduce constants and first order monomials. And typically you wouldn't hear people talk about this in this way. But I'm going to point out that reproducing constants, if you have positive shape functions, defines a partition of unity. So if you're not familiar with the partition of unity, I'll explain it in a second. But the key part of this construction is that we could swap out barycentric coordinates for any partition of unity. That's like the crux of the construction. Is that we're gonna be creative, introduce an alternative partition of unity that's machine learnable, but then turn the crank and do the classical thing. So let's go through the we could first, if you're not familiar with it, a partition of unity is just a set of functions that are positive and sum to 1. And so in traditional numerical analysis, you would think about like indicator functions on your cells, like what you would get in a low order finite volume scheme, right? Those are disjoint cells. Another version that's maybe a little bit more foreign to traditional numerical analysis is that you have a partition of space, but they don't need to be disjoint, right? So this is an architecture that people use all the time in machine learning, that you would take the softmax of a neural network. This is typically used to parameterize like a categorical random variable, right? So you would plug in a point X, and this will return a vector of probabilities that are positive and sum to one, like probabilities do. We're going to interpret this as partitioning up space, right? So for a fixed point, we're going to say this point belongs like 0.6 much to this orange partition, 0.3 much to this green partition, 0.05 or whatever to the blue one. Okay, so I think this is a diffuse partition of space. Okay, so how would you build, given a partition of unity, whether it's barycentric coordinates or one of the fancier ones that we're going to pursue, how would you build low order Whitney forms? So there's this kind of abstract formula that you could evaluate. But what I've done is I've just written it out for the k is equal to 0, k is equal to 1, k is equal to 2 case. Okay, so what you get is that the lowest order Whitney form, the Whitney 0 forms, it's just the P1 finite element space if you start from barycentric coordinates, right? So you get this set of shape functions that interpolates nodal degrees of freedom. The Whitney 1 forms, you get this, right? So it looks like the P1 finite elements, stuff that's like linear combinations of and products of P1 elements and their gradients, right? So that gives you this set of shape functions, which interpolates tangential components of a velocity field at edges. Okay, so a different differential form. And then the two forms have this same thing, right? Again, now you've got some cross products in there, but it's just right, linear combinations of barycentric coordinates and their gradient with some cross products, right? That gives you these shape functions, and they interpolate phase flux differential form, degrees of freedom, right? And you might, especially if you work in electromagnetism, right? These are the Nedelec edge elements. These are the Ravi-Toma face elements. And these are kind of the workhorse for doing electromagnetism. So what's so special about Whitney forms? What's important is that they give you an exact representation of the generalized Stokes theorem, right? Like the Gauss divergence theorem, Green's theorem, fundamental theorem of calculus, and so on. And so what you can see, right, for the 0 forms, you've got nodal degrees of freedom. For 1 forms, you have edge integral degrees of freedom, right? You've got stuff that's like the integral of u dot dl. So if you want to represent the gradient of a scalar field, right? Okay. If your scalar field lives on the 0 forms, okay, and you want to save its gradient as a 1 form, you can use the fundamental theorem of calculus to represent this exactly, right? What we have right here is the degrees of freedom of the gradient, but you can write that just in terms of the difference of the nodal values, right? So you can calculate directly on the degrees of freedom, and what you get is that that the div grad and curl are onto, right? The gradient of a 0 form is a subset of the 1 forms, and this gives you pointwise there's no approximation in div grad and curl, right? It's not like finite differences where you would say like a divergence is to within truncation error. This all holds to machine precision. There's a very deep connection between the graph calculus that I presented earlier and these shape functions, which is that the bilinear forms that you would get in a finite element method, right? The kind of things that would be like grad q dotted with f if you wanted to take the divergence of f case, right? Like a weak divergence. That can be written, sorry, I'm not sure what my pen's doing, just jumping around. You can write this bilinear form as the product of of a graph divergence and a mass matrix of the Whitney forms. And so what you can see is that the mass matrices of these Whitney forms play the role. These are exactly the
Case.
this
Case.
metric information
Case.
that we were solving for previously. There's a lot of details to go through, so maybe you could just take my word for it.
Case.
But what's happening is that the Whitney forms, the geometry of the Whitney forms, right? When you evaluate the mass matrix, that's telling you about the sparsity of the graph, right? The graph matrices are for a fully connected graph. The mass matrix is kind of sparsifying that graph.
Case.
Okay, so maybe some of this is a little bit abstract. So let me give a concrete picture. So what I've shown here is I have a partition of unity. It's these two red functions. You can check that they both, for a fixed x, they sum to 1. Those are the 0 forms, this thing that I've boxed up in red. Now I'm evaluating the 1 forms. Okay, so this is something that you can just evaluate with automatic differentiation. What I'm going to do is I'm going to sharpen up the partitions so that they approach indicator functions on 2 cells. And you can see exactly what the 1 forms give you, right? In that limit where you have 2 disjoint cells, you get something that's like an oriented direct measure, right? And so the 1 forms are the boundary of the partitions of space. And so this is another way that you can interpret this stuff. Like you can think about a finite volume method, right? For a finite volume method, once you have a cell, you can define a divergence as the sum of the fluxes on the boundary of a cell, right? And so our 0 forms and our partitions of unity give us an analogy to a cell. It's diffuse. The 1 forms define the boundaries of those partitions, right? And so we can do this all, as long as we can start from a partition of unity with automatic differentiation, we can get a conservative in the finite volume sense divergence operator, and so on for curl and others. If you want to, not to beat a dead horse, but if you want some extra intuition about where these things come from, you can derive these expressions very simply, right? So if you start with a divergence, you multiply by a partition of unity and you integrate, you apply Leibniz rule. All you need here are the definitions of a partition of unity. So you can multiply by 1 because the sum of phi j's are equal to 1. So that's how you get the second line. This third line, you can add 0 because sum of phi j equals 1 means sum of grad phi j is equal to 0. So you can add these terms in here. And so you can see the Whitney 1 forms pop up. And if you compare this to a traditional low-order finite volume scheme, you can see that this plays the role of something like an area density, right? If you reverse the orientation, psi I j is equal to minus I j I. And if you integrate this thing with a piecewise constant representation of u, you recover exactly a finite volume area, right? So think about these. As long as you can integrate these functions, you will be left with the kind of summation by parts formulas that you're used to in finite volumes, discontinuous Galerkin, whatever. I'll skip this, but I'll just say that you can prove this on an arbitrary manifold. So if you want to do this for surface PDEs, if you want to do whatever, there's fancier versions. Okay, so what we can do now, before in the graph setting, we fit a Hodge-Laplacian to the underlying graph. Now, we parameterize the partition of unity, and that will induce the graph, right? So the mass matrix, just from integrating those Whitney forms, that provides us with the graph and what subdomains share an interface, share a common interface. So there's a lot of discussion now about okay, how do you design a good partition of unity? You want to be able to evaluate a mass matrix That means that you want good quadrature rules. If you just take, we've done a lot of work with a softmax deep neural network. The challenge with that is you end up with a variational crime. One thing that we do a lot that's very concrete, this looks like, I don't know, like a projection-based ROM or something. We start with a tensor product B-spline grid. B-splines, 1D B-splines are a partition of unity. Tensor products of partitions of unity gives you a partition of unity. And then convex combinations of partitions of unity gives you another partition of unity. It's kind of the logic. All right, so we can take these B-splines, right? Like the nodes are trainable, so they can scoot around as they evolve under gradient descent. And then we parameterize convex combinations of these B-splines by having a machine learnable tensor here, which is constrained for each row of the tensor to be positive and sum to 1. And so what I'm visualizing in this column here is the entries of this tensor. And you can see in the right, this gives you these shape functions. Right? So in this case, we have a ton of fine, and just like 12 by 12, something over 100 2D tensor product B-splines, but we can extract these 5 partitions of unity out of them. What's nice about doing this in this way is that you can pull these coarse partitions of unity back onto the fine grid to do your quadrature, right? So that's one option. There's some other options. We do some stuff building them with Gaussians. There's some tricky stuff that you can do and so on, but maybe I'll just leave it at that. So what I'm showing here is that along the top, here are a set of 5 partitions, same here, the same set of 5 partitions. And in this table, you can see the boundary that's shared between the 2 of them, which comes from evaluating the Whitney one form. Okay, so what we've got is we've defined 2 finite element spaces. Right, we have a construction for that, and we have a good way to evaluate their mass matrix. Okay, so now that we've done that, that's what we pop in here for our Hodge Laplacian, and now we can play the same game, where we're going to look for a nonlinear neural network perturbation of a discretization, of a finite element discretization now of the the Laplacian. Right, and we can do quality constraint optimization because the whole framework, all the analysis still goes through, even though we're using finite elements to parameterize the mesh. Okay, so it's a little bit abstract, all this stuff. So let me give some applications to make it concrete. This 5-strip problem, this is a classical example from HDiv finite elements like Ravi Thomas or hybridizable DG like Tom Hughes's group. Did a bunch with this in the 90s and Urif Masood. But the point is that if you have a uniform, as a boundary condition, you have a uniform flux from left to right, but you have a piecewise constant kappa, where kappa is the material coefficients. You have this interface condition that the jump in the flux has to be equal to 0 in between these 2 things, but the gradient of the solution is perpendicular to the interface. So these kind of decouple, right? The way you should get is like 5 strips with a constant flux through each of them, right? And so what we do, we don't tell it where these are. Like it's training data, we just give it a solution to this for what is the true pressure and the true flux. And then we train it and it identifies that the partitions are these 5 strips. Okay, so that's unsupervised, for people without a machine learning background, unsupervised would mean we don't tell it what kappa is. We don't tell it where the partition should be. It's inferring for itself what a good control volume is, such that so that you match the data, the PD constraint optimization. Right, so that's a toy example. This is a big project that we did for lithium-ion batteries. Actually, doing this for real. So what we have in a lithium-ion battery, you have transport through this microstructure. Blue is lithium particles. Orange is a conductive binder that's added to facilitate transport. And the white is an insulated material with structural properties. And so the way this stuff works, there's like 6 orders of magnitude in terms of the different conductivities between these 3 phases, but the transport will kind of trickle through the orange, right? And so in the center here, I'm showing the electric potential. On the right, I'm showing the corresponding flux, right? And so you can see this transport pathway. And so at Sandia, we have CT scans, then we have automatic TEP measures, and these are massive calculations, right? These are, even this 2D picture is 6 million elements. And so you can only do like 1 or maybe a handful of these for a full 3D geometry. And it's really historically just for giving qualitative insight, right? You can't do a design problem. It's too expensive. So what we do is we train the Whitney forms to reproduce this voltage and current plot. And so, but we only give it 8 finite elements, right? It's only looking for 8 partitions. And so what it's doing is it's fitting the partitions to these specific transport pathways. And so we can reproduce, but like a massive reduction in the number of degrees of freedom, right? This is almost 1 million fewer degrees of freedom. And we can reproduce the error to 0.1%, which isn't great. And that, it's like eyeball norm matching. But the important thing is that the conservation law is fit to machine precision, right? So how well you reconstruct the field, fine, but not perfect. The important thing is that the Dirichlet-de-Neumann map is perfect, right? The flux coming in is exactly equal to the flux coming out of these pathways. And so you can couple this to other models and preserve the conservation structure. We can do this for nonlinear problems. This is a nonlinear drift diffusion equation for a semiconductor that we've done some work with. Because you're enforcing physics, this generalizes very well, right? So unlike doing other kinds of machine learning where you need a ton of data to train it, we just did one training simulation, and then it can actually extrapolate pretty far. This is a IV curve, voltage drop on the bottom, log of the current on the y-axis. The last piece is that, of course, you can only scale this up so far, right? Like, if you're looking at like an actual very large scale system, you need some strategy to do this. So what you can do, we just submitted a paper for this that'll be on archive shortly, is you can incorporate this into like a mortar method or a domain decomposition, right? Where you can have lots of these data-driven Whitney forms. In this case, each one of these boxes on the right, and you train it so that each little box can respond to a given trace space, right? Like the Lagrange multiplier that enforces continuity of the fluxes in between the 2 of these. And now you can like glue all of these together like Legos. So if you have a part of your domain that's particularly challenging to simulate or extremely expensive, stiff, multi-scale, whatever, right? You can punch that out, replace it with one of these data-driven elements, but then couple it back to a standard finite element scheme, right? And you can scale up, and we show that we get convergence in a certain sense, right? For these guys, where did it go? For these guys, it's basically you're only going to be able to get as good of an answer as gradient descent finds, right? There's no guarantees there, right? But now you can break it up into smaller problems, and eventually you do get a notion of convergence. Okay, so that's how it works in the forward simulation case. The stuff that we've been working on in the last year is how do you plumb these kind of models with uncertainty quantification. And it turns out that there's a type of representation of uncertainty that fits really nicely with this graph interpretation of mimetic finite element methods. Okay, so probably, I'm guessing in this crowd, everybody's seen what a Gaussian process is. The idea is that you're modeling your data, and the samples of the function you're trying to approximate is coming from a multivariate Gaussian distribution. And so when you condition on known data on the value at a point that you want to either interpolate or extrapolate, you get nice closed form expressions for the posterior mean and covariance. Right, so everybody loves Gaussian processes because they, I always call these sausage plots, right? Like uncertainty small at the data, and then as you move away from a data site, right, the uncertainty gets bigger, and so on, right? So it's modeling the uncertainty during interpolation through the regularity in your data, right? So this assumes that you have nice smooth data. You can use this as kind of a surrogate for an error estimator. This is limited, of course, because you have to calculate a matrix inverse that goes like, so the cost of that goes like the cube of the data that you've got. So this is something that's typically, you can really only use in relatively small data limits, but when you can use it, it's amazing because it gives you like a pencil and paper expression, the uncertainty, no sampling required. Because there's an alternative way, typically you would do this by solving the Schur complement problem. If you're a linear algebra person, this looks like a Schur complement problem to you. There's an alternative way to pose this as an optimization problem. So if you can define what's called a reproducing kernel Hilbert space, which is the span of functions that look like, if you want to evaluate them at a point X, the shape functions look like you take the kernel at the data sites, right? These are the xi's, right? So you're looking at linear combinations of the covariance kernels like this. And so the optimal recovery problem consists of solving this, where this k norm is a matrix in a product, where the matrix is the covariance kernel, right? And this looks like I would like to match my data. Right? I want to find an f that approximates y. Plus, there's this regularity penalty. So you're penalizing in this RKHS norm, but you're saying you want a smooth reconstruction, right? You're trying to solve this. It's a multi-objective optimization problem that you're enforcing interpolation through this penalty weighted by 1 over epsilon. So if you break this down into linear algebra, you can get this quadratic program that you can solve. And because it's a nice quadratic program, you can write down pencil and paper what the minimizer of it is, and you get the exact same expression that you would usually get by doing a Schur complement problem. Right? So it's just an alternative way to recover the posterior of a Gaussian process, but through optimization. So the nice thing is now that it's optimization, you can add equality constraints. So what we do is on every edge, now instead of having those nonlinear fluxes be deep neural networks, now we're going to have them be a GP. So each edge gets a Gaussian process, which we solve for by solving this optimization problem. But now we enforce, for example, that the sum, Kirchhoff's law, or the conservation balances that we have. So what's really nice about doing this is after enforcing the constraint, it's not obvious, but when you enforce this constraint, you still get the nice analytic expressions for the Gaussian processes at the end of the day. So you have to solve the KKT system to enforce this constraint at training time. But then when you're doing inference on the model, right, like you've extracted your data-driven model, you're going to make a prediction on it, you can just trivially evaluate the uncertainty and the fluxes and the idea behind it. There's also some fast solver kind of things that you can do. We have this block coordinate descent strategy. The idea of block coordinate descent is, you don't try to optimize all your variables at once. We're going to optimize over some subset of the variables. In this case, it's going to be flex degrees of freedom and a nice equality constrained QP pops out that you can solve analytically. So basically what that means is for the unknown fluxes, the same thing happens with DG, like that you can do this nice Schur complement problem to solve for the fluxes at element boundaries without needing to know what's going on inside of a DG element. We get the same thing here. We can get the currents on the edges that's consistent with the boundary conditions without needing to know what the actual voltages are, what the zero forms are. So
Is-
again, that's probably something that I have to go through a lot slower to totally get the details across. But let me show some examples just so you can see what these look like. So we've done this on subsurface fracture network, this kind of problem, right? You're talking about nobody has any idea what the actual fracture geometry looks like because you're talking about subsurface flow like miles down into the ground, right? So in this case, we get data about what's happening at the surface, and now it's really important that you actually get an uncertain representation of what the flux is. Could be because you don't even know where the fractures are. We've also done some work looking at arterial blood flow, also at circuits, bipolar junction transistors. So what you can see is for a BJT, this is like a kind of transistor. It's a very challenging problem. So what I've shown is data, which is these blue dots. So these transistors have, at large currents, they behave like a resistor, like the current scales linearly with respect to the voltage drop. For small voltage drops, they behave like an ideal diode, so it scales exponentially. And so in order to actually recover the current voltage relationship for a device like this, you're talking about data that scales, you can see it here. The scale might be small, but this is 12 orders of magnitude. So what you could do, like if you want to do this intelligently, you want to do a log scaling of the data, right? There's no way that you can train something at 12 orders of magnitude difference in the data with gradient descent, right? It'll just sort of choke on that because it's multi-scale and you have no second order information to calibrate the step size. But we intentionally left it in here so we didn't do a log scaling, and you can see that the GP posterior tells you it knows what the model doesn't know, right? So you get a nice tight representation of the uncertainty until you get down into this very, very small current range, but that you get a good uncertainty bound that actually gives you a relatively tight estimate of how poor your fit is. Maybe I'll stop there. I've got some other material about using all this kind of formalism in order to fit dynamics. But I'll stop there. Yeah. So the point, all of this stuff is really just kind of foundational plumbing, right? How do you build finite elements with these sort of guarantees? The point is that now you can take these you can build models if you can generate enough data, which is a caveat, right? Like you can't get it for free. You need a big data set of like high fidelity simulations, same as like a reduced order model or anything else, right? But if you can do that, now we can extract something where that can make a structure preserving prediction of a device basically in real time, right? That for a lot of applications, it makes sense that you could extract maybe 10 degrees of freedom that really encodes the whole picture, how fluxes are being transferred across the device and so on. So maybe I'll stop there and take questions if there are any.
Hey, thank you very much, Nat. Very much. Let me give you some virtual mapping. This was really impressive. Lots of connections, lots of very familiar things. We call this discrete gradients, discrete curls. This matrices are very familiar to us. Questions for Nat?
Hi, very nice talk. You touched on sort of two different approaches. One was using neural nets to build this partition of unity, and the other was to use Gaussian processes. Can you comment on when you thought one was more useful than the other, or advantages and disadvantages?
Yeah, we more or less, we started with neural networks, and within the last year, I've been pivoting completely to the Gaussian processes, mostly because it's new. You need to do new things. But mostly because we've been focusing on uncertainty quantification for the applications that we're looking at. It's a little bit painful for the Gaussian processes to set everything up. Like the plumbing for implementing these models in TensorFlow is actually really easy. If it's neural networks, it looks the same as a graph neural network if you're familiar with a graph attention network. And that's the beauty of TensorFlow is you just like, I don't know, you hook the pieces together and it does it all for you. With the Gaussian processes, it looks a lot more like traditional scientific computing, that you have to deal with, setting up these global matrices correctly, sparse linear algebra, doing everything efficiently, and so on. I like the Gaussian processes because there's no hyperparameter tuning like you have in a neural network, right? Like, if you have a neural network representation of the unknown flux, how do you choose how wide? How do you choose how deep? What activation function? What learning rate? What that? It's like never ending. Whereas Gaussian processes, it's like, there's like a couple parameters you have to wrestle with, but it works for you. Like it does you just turn the crank and it works it all out. So you do hit this large data bottleneck eventually for the applications we've been looking at. We're looking at moderate size data, like tens to hundreds of examples. So, super application dependent where a given problem would lie and what the better one would be.
Sure. Thank you.
Hey, Frank.
Hi, very interesting talk. Thank you. I have two questions. The first one is, at the end of your first talk, right, you have kind of a constraint optimization problem, and you have the neural network embedded in your constraint. Do you actually have to solve that? And if so, how do you solve it? Yes, yeah, basically, yeah.
So you impose that the model holds with a Lagrange multiplier.
Okay.
And you would do the usual thing you do in PD constraint optimization. So the KKT condition, there are three kinds of derivatives that need to be equal to 0. The derivative of the model with respect to the solution, with respect to the Lagrange multiplier, and with respect to the model parameters. And you do them sequentially. So the derivative with respect to the Lagrange multiplier being equal to 0 means solve the forward problem with the current set of model parameters. So that's like a Newton-Raphson solve with the current set of weights and biases in the neural network. Then you have to solve, derivative with respect to the solution is equal to 0, gives you an equation for the Lagrange multipliers. That's actually it's an adjoint equation. So it's a one-off linear solve. You take the transpose of the Jacobian of the nonlinear equation, and you just get a linear solve for that. Now that you have the solution and the Lagrange multipliers, you do a step of gradient descent to update the model. So basically what that's doing, you can think about the manifold of solution, Lagrange multiplier, and physics models, right? And you want to search along the manifold where the physics are satisfied exactly. That Lagrange multiplier forces the gradient descent step to be along in the direction, like along the tangent space of that manifold, right? It's a lot in the direction where the physics are still enforced exactly. So you don't need to do that. You can do it by penalty. There's all sorts of other things that you can do, but for us, that was the setup that was the fastest.
Okay, but you do use like the first order derivative of your network, right? The MV there.
Yeah, the only information you need is first order derivatives of the neural network. Right. So as long as you can get that with automatic differentiation, like I do this in TensorFlow.
Okay.
There's no Hessian information or anything like that.
Okay, yeah. So it's like an augmented logic. I have a second question really quick, which is when you did the Gaussian process, you mentioned every edge needs to be a separate Gaussian process. Is that correct?
Correct.
Wouldn't that be because I know Gaussian process has kind of a scalability issue. Will you be running into that issue? If so, how would you resolve it?
Each edge gets a Gaussian, but these are like without the equality constraint. Let me pull up let's see. There's a good one.
All right.
So without the equality constraint, without this thing right here, these would be decoupled Gaussian processes, right? If you didn't do that. So then you would have number of edges decoupled data by data systems, right?
Right.
Now that you couple them together, it's a block diagonal system in the top left block of your KKT system, right? Where you have each individual block would be the covariance matrix of the data. And now in your constraint block is just something that is number of data by number of nodes. Sorry. So at the end of the day, when you do the Schur complement, which is how we actually solve it, you get the same complexity, right? You get something that's still like data by data to solve for the Lagrange multiplier to enforce the constraint. And then the back solve for the top left block still reduces to something that's number of data by number of data, right? You can exploit the block diagonal structure to it. I don't know if that makes sense, but so it doesn't hurt you any more than a normal Gaussian process would.
Right. It's just a number of them now, right?
Yeah. I mean, so you got to pay for it, right? you got to do linear algebra, and in some ways, that's I'm a computing person, so that's what I like about it. But yeah, it's not like you get it for free.
Okay. Thank you.
All right. Golo, do you want to ask your question?
Yeah, I'll ask you a quick question. Thank you, Finite. I have the question about structure other than mass conservation. So, for instance, in this one problem you showed about the divergence of kappa times the gradient or so, where you try to find what kappa is. Can you show that slide?
All right.
Right, that one exactly. So then in here, you'll probably have also something like some kind of energy dissipation going on, I guess. If it's,
I mean, this is just Darcy flow, right? So there isn't really an energy to this problem. It's a pure mass conservation problem.
I see.
Right? This would be like divergence of mass flux is equal to F, and the mass flux is a gradient of the pressure.
All right.
I see. Okay. So I guess that would only come into the play if you had a time derivative of find 2.
Well, for this one right now, if you're looking at
all right,
drift diffusion equations, right now you have nonlinearities, you have advection, you have diffusion, and so on.
All right.
And in principle, you can do, this gets to the part that I kind of blew off where, okay, it's one thing to enforce conservation structure, and you can enforce conservation of mass, momentum, energy, like whatever you want. But if you want to identify a bracket,
all right,
and you're talking about dynamical systems, that's like a whole extra dimension that you can bring in these kind of tools, and you can do stuff, but it's, there's extra machinery that has to go on top.
I see. Okay. Thank you.
So now I know that you are focusing on kind of smaller problems, but do you ever have to all right, solve systems with these operators, like for example in the electromagnetic case, that can benefit from preconditioning? All right.
We do, but I don't know that I can talk about the specifics of them.
All right.
For sure, like electromagnetic waves for domain decomposition.
All right. So you don't need to go into it if you can't, but the reason I'm bringing it up is we have these preconditioners, AMS, ADS. They're basically just requiring the discrete gradient, the discrete curl operators. They are very algebraic in nature, and I'm 90% sure that they will just work for this neural network constructed operators. Just so you know.
Yeah. So maybe what I can do is this. So there's we haven't figured out it's obviously something you can do with this.
All right. All right.
I'm not, I use multi-grid. I wouldn't call myself like a multi-grid person, but there's a nice observation that you can make.
All right.
It's going to take a second to load the PDF.
All right. All right.
But
All right.
structure for these chain complexes, there's hierarchical structure. So if you take a chain complex and then you refine it, let's see, I'm almost there. It's
All right.
yeah, here we go.
All right.
If you have like a fine graph and a coarse graph, you can define restriction and interpolation operators between the two of them, right? And kind of exactly like if you had like an AMR code, you know what I mean? Like where the nodes of the coarse graph are all fine nodes, but the fine graph has extra nodes on top. So you can always just evaluate the coarse solution on the fine graph with some interpolation for the held out stuff. So we talked about this a lot, right? That like if you have AMG and you have a hierarchy of nested complexes, that for sure you could train like the coarse one to match the fine one, right? And by construction,
All right. All right.
everything would be conserved across the hierarchy, right? That's the point of this this kind of like pair of commuting diagrams, is that you can do all of this and preserve structure across them all.
All right.
Yeah,
I was you can do that. This is not what I was referring to.
Okay.
See if I can say it differently. Once you have these discrete operators, you can discretize, but you can also solve efficiently all the diffusion problems with algebraic multigrid. Let me put it this way. We have solvers that only take those operators, and for example, reduce the H curl diffusion problem to H1, and then H1 is just treated with the MG, and that's usually very efficient. And same for HDiv.
Yeah, that's what, like, it feels like you could train a model, a coarse model, to reproduce a fine model and use that as a preconditioner, right? Like that seems
also,
like
yeah.
it would make sense to do. I don't know how competitive. I've personally stuck, because I'm more of a physics and modeling person.
Yeah.
I've tried to stick to the setting where there's unknown physics and you want to extract a model from experimental data. I do think that there's in this preconditioning setting, I've talked to Eric Sear, he's a collaborator of mine. He's a multi-grid person. We've talked about this a lot, but I haven't found a collaborator yet who's, so maybe if there's anyone in this audience that has an interest, that's something I think you could definitely do, and it makes sense, and I have ideas about how to do it, but I don't feel authoritative enough to take the plunge myself.
Yeah, understood.
Yeah.
Okay, other questions? Anyone? Just pick up.
I will say, I'm happy, especially I've just come to UPenn. I'm feeling separated from DOE, so and looking to maintain connections and ties and so on. So if anyone wants to reach out and talk, if you have ideas, or you just want this is probably a lot of like pretty technical stuff. If you want to go through it more slowly, one-on-one, whatever, please feel free to send me an email. Happy to talk anytime.
Okay, thank you. Yeah, this is a lot of information, but people will absorb it. They'll watch the recording and they may reach out. This was kind of all low order terms and finite elements, if you want to think about them that way. Have you thought about high order? Is it of interest at all?
Yeah, it's a really good question. So I'm part of a SciDAC where we're developing these for stellarators and tokamaks. And I've been looking into Whitney form construction where you use maybe like a high order spectral basis. That's more for convenience than, I'm not sure how to think about whether there's any value to a high order method, because it's not like the way this stuff works is you intentionally solve on a coarse mesh and you use the data to tell you how to get a good answer. It's not like normal finite elements where you want to refine and then you're guaranteed and then a higher order method will make it converge faster, right? For us, we cheat and the data tells us the answer and we back out, right? So it's not clear up front whether working with higher order Whitney forms would be beneficial. I personally like higher order methods, and so it's something that I've wanted to do, but I've held off on so far just because it's not obvious that it will make a difference, and so I've stuck to the like the lower hanging fruit so far.
Understood. Yeah, I agree with you. I was just curious.
Mm-hmm.
All right. Well, thank you again, Matt. This was great. I'm sure Edge will follow up. We give you another round of virtual clapping. We will post the slides and the recording on the website. And have a good day, everyone. Thank you.
Thanks again. Take care.